So previously we talked about reduction. We could reduce the double bond using hydrogen gas and some metal catalyst. By syn addition mechanism, you add two hydrogen atoms by breaking pi bonds, and you form two stronger sigma bonds. In exothermic reaction, you can form alkane like this. Before we jump into the oxidation, it's good to review a couple things. Think about like how you get to alkene from alkane. Can you connect a couple reactions for it? Well, you know you form alkane by elimination, and elimination requires either halogens or alcohols. So the halogens, you can do easily E2E1, you know, strong base, somewhat bulky ones for E2, or you know, bulky weak base with the high, you know, elevated temperature for E1. Or you can use alcohol to get there by using sulfuric acid at high temperature. Then you can do elimination. Then the question remaining is, how do you form these things? Well, one thing you remember is though, from here to there, you can do it easily by radical reaction. And you cannot do substitution of OH, replacing hydrogen here. So you must go through this step first, then you do this. And since the carbon here is sterically hindered, it's not a good idea to think of bimolecular reaction. So I would do heating up to release the leaving group, then put weak base for SN1, water. So in SN1 reaction, you can create alcohol. Then from there, you can eliminate OH and beta hydrogen in elimination reaction to get there. And also, it's a good idea to think about how do you form halogen on less substituted carbon or even OHs. There. Well, you know, you cannot put these things on the less substituted carbon if you start from there in the halogenation, radical chain reaction. So you must get there. We practiced it a couple times, but it's such an important concept, so I'm repeating again. By doing all of these, you can get there, and from there, it's easy for you to form these things by doing anti-Markovnikov addition, right? This way. This reaction is for this step right there. When you're examining what's happening when you do anti-Markovnikov addition, for this carbon, in terms of oxidation and reduction, this carbon is gaining hydrogen, right? Just like you do in this step in the hydrogenation, which is a reduction reaction. This carbon is getting reduced from 0 oxidation state to -1. If you look at this carbon, this was a -1 oxidation state. Now it's a +1. Same over here. And here for the Markovnikov reaction from this double bond, and it's opposite now. This carbon is getting reduced. this carbon is getting oxidized. Same for this compound. So you should get used to the keeping track of oxidation state in addition. Also, of course, for the elimination and substitution and rearrangement as well. Like I said, oxidation and reduction is not the elementary reaction type that happens all the time, whatever type of reaction you are doing. So the remaining reactions for addition reaction will be the oxidation reaction, especially the oxygen containing chemicals. So I ask you to remember what these chemicals do. So let's start with MCPBA. MCPBA looks like this. This is the benzoic acid, like benzoic acid. Then the P represents peroxy, so one more oxygen, peroxy, benzoic acid. Then you have a chlorine on meta position. So I should tell you where the meta position is. This carbon on the ring where the substituent is, next door you have ortho. So this position here, that position there, you call it ortho. Sometimes they only use oxygen, O to represent the ortho position. This and this next to the ortho, like 2 carbons away from the substituent, that is called a meta, or just M. The next carbon subsequently is called a para, or just a P. In IUPAC system though, we use number 1, 2 for the ortho, 3 for the meta, 4 for the para. Okay. So, you know, on the meta place, you have chlorine. This is your MCPBA. As you notice, this area here has a weak bond, like a peroxide. These lone pairs repelling, that weakening the sigma bond here significantly. So you expect the bond break here, whatever the reaction that this chemical is involved. Then you can also see this portion right here, you know, this ring structure included. This could be decent leaving group, because when you put the electron, dump on the electron, you know, dump the electron on the leaving group, then the negative charge on the oxygen has a resonance structure by the this carboxylate, and having chlorine and the benzene ring is helping it stabilizing the charge further. So this will be a good leaving group. That gives you a chance for this oxygen get attacked by nucleophile. That's the nature of MCPBA. So when you put any type of pi bond, the pi electron, loosely held pi electron, act as a base again, and the electron will be given to this act as a nucleophile, right? So given to the oxygen, and this bond indeed breaks. And as a product, you form this carboxylate, the benzoate, metachlorobenzoate as a leaving group, and plus you are forming intermediate of this chemical, which is Okay, for drawing, I'm gonna have to fix here. I'm gonna have to remove this thing. So let me redraw this. Okay, the product would be this with hydrogen positive. Then you can say this oxygen is able to remove the hydrogen to make epoxide as product. And I hope you notice the changes of the geometry on the sp2 carbon, now sp3. So you can think of this as a stepwise reaction like this, but in real life it is a concerted reaction that happens at once, forming this. So that I'm gonna show you. This is more intuitive in learning the mechanism, it makes more sense, but in reality this is more giving more stable transition state, making the reaction faster. So let me draw this for you. This pi represents the ring with the chlorine on it. So as the electron here start to flow, okay, the mechanism is not giving pair of electron at once. The real happenings in the flask is charge, the particles start to migrate and get some time around this oxygen, making the oxygen more unstable. So electron slowly move away to the oxygen, then that oxygen is next to the partially positive carbon here, so they move to the bonding area slowly. As it flows more and more, this flows away more and more into this more and more. Then this carbon feels uncomfortable, so electron here, the pi electron, like to move away from the carbon, so going to the oxygen more and more, but then they feel hydrogen next door. So electron eventually coming here to form bond. That makes this electron move to the oxygen. Okay, so happens like this. So the more it comes into the MCPBA, the more of these arrows taking place. So if you look at it, these two carbons with the do I have any other color pen? So these p orbitals making bond with oxygen like this, forming epoxide at once. I mean gradually, but they're forming two bonds at once with oxygen. Then this bond breaks to give oxygen to the double bond, and this turn into the double bond, this turn into single bond. Then oxygen is making a sigma bond with the hydrogen, and hydrogen lose a bond with the oxygen. So this much is becoming independent molecule, just like you saw in the stepwise mechanism. You are forming this plus this as a final product. So you got your epoxide formed, and that oxidized two carbons. So it is addition because you added just the oxygen there without losing anything, but you also oxidized it. The next oxidation state I want to look at with you is osmium tetraoxide. The reaction condition will be given in various forms on the tests, but they're normally like giving same product. Some case they give you only osmium tetroxide. Sometimes they give you more conditions with it, but I normally believe that they meant same. So you don't need to worry about the the presence of other chemicals. So let's take a look at the mechanism. When double bond is facing osmium tetraoxide here, it looks very similar to the sulfuric acid with the 8 bonds. And that means the osmium has a +8 oxidation state. 8. So osmium, due to the oxygens, it became very electronegative and ionic. So it wants electron. It means osmium tetroxide is acid electron acceptor. But in terms of oxidation and reduction, osmium tetroxide is oxidant. It is getting reduced, getting electron. But the partner, in this case, the double bond, is losing electron due to the high plus charge on the osmium. So the double bond is getting oxidized. Therefore, the double bond again is acting as a Lewis base. So what happens is some of the empty d orbitals of osmium is receiving the electron. We can imagine some d orbital here, okay, and that is filling up with the pi electron that's given by 2 p orbitals of atomic orbitals. Then the osmium is getting too much electron. Already it has like 10 plus some d orbital electrons. So what happens is these electrons in the pi bond here, it's pushed away to the oxygen that's electronegative. Same here. As it goes here, what happens is the double bond is losing electron, so both carbons becoming more partially positive and attractive for electrons. So gradually again, electron moves to the carbons from double bond to the oxygen, but right away to the carbons. So here you should be careful. The electron given by the pi is not making bond with osmium because in the middle you don't have any atom. You gotta choose which carbon makes bond with the osmium. However, it's not the osmium, they are the oxygens already forming bonds. So the electron density just moved to the osmium and they are the one making bond. There has been a study to see if it makes sense to assume that the carbon makes bond with the oxygen and then the other carbon making bond with the osmium, just like the double bond making a bond. And there has been extensive study, but some evidence support this mechanism better. So I'm showing you this one. Then what's happening is, as these group of atoms pushing from the bottom, reacting from the bottom, you saw this before, but these groups are pushed up. If they react from the top, those groups on the double bond are pushed down. So you have to still think of the two possible reaction modes, okay? So you got this, and these 3 methyl groups pushed up, and they are going 3-dimensional now into the pH. Then oxygens from the osmium tetraoxide form the sigma bond using this electron pair and that electron pair. Then here you don't have any more pi electron. It's all in the osmium, and that lost two pi bonds with the two oxygens, and you still have this. So there, osmium has a +6 oxidation state. So, you know, two electrons moved into the osmium. Where is it from? According to the mechanism, you know, it's from the pi bond. So on the test, they give you osmium tetroxide alone, or sometimes they put pyridine, or they give you actual drawing. Then from the second step, this is a step 1, okay? Step 1 with osmium tetroxide and pyridine. Second step, sometimes you see only water. Sometimes you see, let's say, sodium persulfite. Or sometimes they give you MnO. MnO represent some weird looking chemical. So like N-methyl. On the nitrogen you have a methyl. And this whole thing is morpholine. And this is always in the equilibrium in the reaction with the negative and positive. So an oxide form. Okay, so these maintain the osmium tetraoxide. So together they're keeping the reaction running. So any cases, you can assume same things taking place. So let me use the simpler version of the mechanism to make you feel better. Let me use water. All right, so the water compared to this chemical is basic because osmium is in 6 oxidized state, highly positive, very acidic, very electron attractive. So this is giving electron to the osmium and breaking a pi bond. Very congested, right? So here you can take different mechanisms, depends on the pH, but in the basic form it's not easy to have this form, so let's do this first. I apologize for not able to go through the detail because then it's going to be very lengthy discussion. Like this. Then this basic oxygen can easily pick up hydrogen. Yeah, one can argue it may not happen internally, but rather by a solvent. This will be taken off, and then, you know, the solvent shuttle the hydrogen to this oxygen and do that. But I don't like to get into that discussion, and I like to make the discussion simple for sophomore organic people. So you got this ring with a hydrogen, and now this one's a positive. There you have negative. Then you know this one's not quite stable, so it like to have a resonance. Then due to the electron negativity of this oxygen, this breaks off to make it OH. I think I need to save some space here. Yeah, so I formed one oxygen here, OH, I'm sorry, hydroxy. There you have OH. Well, I like to point out though, any of the osmium, they're not flat structure, okay? When you have to discuss the real geometry and everything, you know this osmium has sp3 hybridization with a 4 double bond. I hope you're not the type of person memorizing hybridization by a presence of the double bond or triple bond. I hope. You have osmium case, you have 4 sigma bonds and the 4 unshared orbitals. So to have most stable hybridized orbital, you need 4 orbitals. So it's sp3. Those double bonds are formed by the d orbitals of the osmium and the p orbitals of the oxygen. So I don't want to digress too much, but I just wanted to point out. So here you can also go a couple different ways, but again, in the basic solvent, base can take off this hydrogen and then make this process faster. Like this, oxygen is able to donate electron and then do this in the basic, okay? If it's acidic solution, then you're gonna have to have hydrogen putting on the oxygen first and take off the hydrogen here and then do the resonance. In the neutral pH, then you may have to use water, because we are doing this mechanism with the water, have a water attack on this one and repeat sort of kind of this process for breaking this off, just like we did over here. Anyway, so if you do that, then you know you got alkoxide with the OH here, with osmium trioxide but with the hydrogen on it, right? And this oxygen is positive, so this is able to attack here and break this oxygen off. Let me show you properly. Yeah, here. Then finally, you know, our product out of all this lengthy mechanism is diol. So here you had double bond on each carbon of the double bond, you added OH, so it's 1,2 diol. Then earlier I mentioned that you know, this MNO maintained osmium tetroxide. So out of this reaction, you see you have a trioxide osmium, and this will react with this and take one oxygen from it, and you regain. So by reacting this with this, you regain this, so you can continuously react. And this thing, after losing oxygen, you go back to regular NMO. All right. So reduction, giving you alkane from here, and oxidation, MCPBA. You need to memorize. You got epoxide, then osmium tetraoxide with the second step to break off the osmium off of the carbon. You get 2 OHs. But as you saw in the mechanism, the OH happened to be on the same side. So this is another example of syn addition. Then people can ask, can we make anti-diol, not syn-diol like osmium tetraoxide? So indeed you could. So always I tell people, as a scientist, you should not think something is impossible. It may not be, but our attitude has to be to, you know, at least solve the problem coming to us. At least the scientists should not be the, we're not in the position saying, oh, that cannot be done. No matter what the challenge might be, our attitude should be, yes, we will, and we could do it. And that has been attitude. And I don't like people doing science having, you know, attitude like, I can't not do that. There must be a limit. Those are exceptions. And, you know, currently we are facing this pandemic, and I don't want to have people doing science with that mindset that I cannot do this. Then who's gonna do this and save the world? You don't have to be a hero, but I don't want people around me having that attitude anyway. So how do you get the anti-addition? We can use this epoxide. So remember, anti-diol. We can use this. How do you do it? We can put acid and the water. Remember, this is the condition to add OH here on the double bond in the Markovnikov mechanism, and you get the OH in the mole substituted, and the hydrogen goes here. So same condition, but depends on the reactant. You need to remember you get the different product, obviously, so you don't attempt to memorize. I always ask you to know the principle. So what do you do here? Well, the base, the solvent reacting with the acid, so you have H3O plus like here. So oxygens holding 3 hydrogens and becoming acidic. Then you found the base, giving electron to the hydrogen and giving off the water as a leaving group. Then the epoxide forming this. And I hope you remember in this bridged intermediate, the bond with a more substituted carbon that can bear more positive charge needed less electron density from the fourth bond becomes very weak. So oxygen of water acting as a base coming from the backside of the leaving group, breaking off OH, not completely off of the molecule, but from the off of the carbon. Yeah. Then you get this OH sitting down here, and then those two groups pushed down, and the water stays up there in anti. Then another water molecule, there are plenty of water as a solvent, attacking hydrogen and giving electron to the oxygen. Then, excuse me, you can form anti-diol. Sometimes as you turn around the single bonds, you get the same compound, same RS. But other cases, you could have different products. So it depends on the case, but you need to always check on it. So anti-addition. If you consider addition from this double bond, you have two OHs added, not like this, but this way you get the anti-addition. So always to contrast them and remember them. Here comes more though. Similarly, you have a potassium permanganate. The mechanism is similar. If you keep them in cold reaction, it gives you same diol product, syn. Okay, same mechanism, same kind of product. But this reaction is heat sensitive, so if you raise the temperature, then something extraordinary thing happens. You get, let me use different color. You get this. This. So what's happening here? Okay, let me try to squeeze in this box. So you have the double bond and manganese, then electron comes, this goes to the partially positive carbon. You can check the previous mechanism with osmium tetroxide, and you are getting same type of intermediate. Okay, that's good. Here, if the temperature were cold, with water or hydroxide, presence of other chemicals, you will end up breaking here and here, and you get diol, 1,2-diol syn addition. But when you have more temperature, heat, then the vibrations of the ring, making the ring very unstable, and then electron has the more chance to jump up to the sigma star orbitals. So you can see that you have partial positive charges here and partial negative charges there, with a +5 oxidation state on the manganese. This electron usually will feel more pi bonded to the manganese, but with all kinds of momentums they do break the conjugation here sometimes, and that moment this can be attracted to this positive charge here, forming, attempt to form double bond there, meaning this bond must break away. But this electron don't like to go to carbon. It wants to be in the bonding to be most stable. That means this oxygen is getting too much electron, over 8 electron for second shell. So this electron pair must move away. So this goes to the shell, the d orbital. So the electron is gained by the manganese. Therefore, this electron feels more repelled, ended up going to the oxygen here. So according to those arrows, you can see you have, oh sorry, I broke this bond. Let me do it again. I'm so sorry. So I have these two having double bond, right? And then this guy lost the bond with the carbon right there. So I have this one. Then you broke the bond here and here. So what you have is a MnO2 all by itself. So that's when you have a brown precipitation for the, permanganese test. So what happened was you literally scissored the double bond out, and you have a 2-methyl and a carbon here, 1-methyl and hydrogen, the carbon. Then after breaking this bond, these oxygens right here, they happen to form double bond on it. So here, you got these 2 oxygens rip off of the manganese. So there you are. You got the ketone and aldehyde. At this point, I need to review something with you. There. So I made this cheat sheet. So from your general chemistry again, I hope you can figure out this as a primary alcohol. The OH is on the carbon with 1 carbon on it, 2 carbons on the alpha carbon, so secondary. Alpha carbon has a 3, so tertiary. And if you attempt to oxidize this with any kind of oxidizing chemical, in this case such as a KMnO4, you can go to aldehyde by losing one of the hydrogens and on the carbon and one on the oxygen, instead forming double bond, and you got the aldehyde. Further oxidation attempt will give you carboxylic acid, meaning you still lose hydrogen. Remember, you lost 1 hydrogen to be oxidized. You lose hydrogen, and instead you get 1 oxygen. Here you got 1 oxygen double bond to 2 oxygen double bond, 3 oxygen bonds. So you lose hydrogen, instead you gain more oxygen bond. Okay? In order to reverse with reduction, that's the symbol. So in the reduction, you are gaining hydrogen by losing oxygen. You gain more hydrogen to gain the more hydrogen by losing the bond with the oxygen from double to single. So you got the carboxylic acid going to the aldehyde, going to the primary alcohol, and the vice versa is possible. Secondary alcohol attempt to oxidize, you end up getting ketone by losing hydrogen, gaining the extra bond with the oxygen. Reduction, you go back by adding hydrogen and breaking the bond with the oxygen. That's a reduction definition. But usually we cannot oxidize the carbon without hydrogen. But we have in Orgo-2 some reaction that's able to oxidize it to the carboxylic acid or ester. Okay, so that's Born-Oppenheimer reactions there. You can get ester, and from it you can eventually go to the carboxylic acid, just like this case. So in principle, we can oxidize the secondary alcohol all the way to the carboxylic acid, but that needs special reagent. Tertiary alcohol, you cannot oxidize it, there's no hydrogen. So with that, we got the double bond, and you oxidized it with the KMnO4 hot, and you end up getting here one side ketone, the other side aldehyde. And I don't want to do mechanism of aldehyde going to the carboxylic acid, but you get the point on this cheat sheet, right? The aldehyde, if you oxidize more, in this case KMnO4, you can make the carboxylic acid. But this portion here had a 2-methyl group, so you still have it, and you have a double bond with the oxygen from KMnO4, so this ketone stays. So your final product with this would be this and this. Okay, so there we go. There is more option for you for oxidation. You can do ozone, ozonolysis. Ozone, you bubble in, you break the double bond. it is going through this intermediate that's awfully similar to what you have seen, this one. Then eventually you are forming these pairs. And I'm not gonna do detailed mechanism, but you can remember, just like a KMnO4 hot, ozone's cutting the molecule in half where the double bond is, even triple bond, then you get the fragments. Those fragments should be their own maximum oxidation state. The carbon with a 2-methyl should get only 1 oxygen, right? Because that's a maximum number you can have on the carbon. So that's the terminal oxidation state, ketone. But for this side, if you first form, you know, you get the aldehyde, then aldehyde, you should remember it can go further. So you get this carboxylic acid. These are considered strong oxidants. So they go all the way. KMnO4 is, as well as osmium tetroxide, is considered weak oxidant. So they go one oxidation and they stop. But they say, do we have something in the middle? Not diol, not carboxylic acid, but can we have something in the middle, such as this? Can we stop at the aldehyde? So like I said, the scientist's attitude is, I'll try, I think I can. So obviously people came up with the method. You put ozone in the first place. Second step, you reduce the oxidation power of the ozone by adding some reducing reagent, such as a metal. You know, metal is good electron donor, so it's reducing. It is destroying ozone and reducing power of ozone in oxidation. Or you can use some sort of dialkyl sulfide, and sulfide is also good nucleophile, giving electrons away easily. Then you can still cut the molecule and you still put the double bonded oxygen, but they don't go to the terminal, they stop here. So ketones anyway, terminal oxidation state for the 2-methyl group compound, but this aldehyde could have gotten the carboxylic acid state, but because of the second step, you stop here and you keep aldehyde. So these are very similar. That's what makes the oxidation with the oxygen in it make it very difficult for student to study. Please compare them and see the precise usage of each conditions. So I think I covered most of the important oxidation states, oxidation reactions. Well, so not soon, but eventually I'll put some more other type of reactions around double bond. But next video probably will be on synthesis. So until then, keep up the good work. I'll see you later.